Okay, let's go through this handout. Hopefully you had some success in thinking about how we can make this measurement on a vector field. This is a very general situation, and some people can be made a little bit nervous by diving into sort of an abstract question like this. And that sort of discomfort is normal. So if that happened to you, don't worry about it. It's not unusual. You shouldn't feel bad about it. That's part of what, that's just part of the deal when encountering new mathematical ideas, especially when we don't have a particular example in hand. So, by asking these questions, I'm asking you to synthesize a lot of things about calculus. So that is a difficult process. So don't worry if it feels difficult. It's because it is difficult. Anyway, okay, so on number one here with these one-dimensional vector fields, if we're trying to measure how much the vector field is flowing towards or away from A, so for the first example here, this vector field is definitely flowing away from A, it looks like, right? To the right it's flowing right, to the left it's flowing left, so this is flowing away. Okay. For B over here, this is definitely flowing towards. Okay, and for C, well, for C it's a little less obvious, but if you imagine, right, that these vectors are telling us how some fluid is flowing across the line, well, it looks like to the right of the point A, fluid is flowing away very quickly, but to the left, fluid is flowing into A only slowly because this vector is shorter, right? So in total, kind of on net, there's more flowing out than flowing in, so fluid is flowing away from the point A here. By the same token, for this example D over here, it looks like fluid is flowing into A a lot, but out of A only a little bit, and so in general, fluid is flowing towards A, not away from A. Notice that these vectors over here, far away from A, really didn't play any role in our analysis of what is happening near A. Right? Really, we're only interested in what is happening very close to the point A to answer this question of whether fluid is flowing away from A or towards A. Okay, so now let's estimate, is this scalar function that is the only coordinate of our vector field, is this increasing or decreasing at A? So for part capital A here, I should maybe number these instead of letter them because it's confusing to have a point called A in example A. Anyway, so to the left of A, M must be negative because this vector is pointing to the left, right? So M is negative over here. To the right of A, the vector is pointing to the right, and that means this coordinate function must be positive. So M is positive over here. So as we go through A, M is going from negative to positive, so the derivative of M must be positive here. So should I write that up here or down here? Let's write it down here. So for example A, this derivative partial m partial x, it's positive because as we move in the x direction, the function m is increasing. Now, even though m is a function of one variable, I'm writing this as a partial derivative because, of course, we're going to, later in the handout, we switch back to thinking of m as a function of two variables, and we're thinking of it as a function of one variable just to simplify things to get this whole thing started. Okay, so let's look at example B and think about the derivative. Well, now m is positive to the left and negative to the right, and so m is actually decreasing as we move rightwards, so partial m partial x must be negative, right, because m is decreasing. Okay, for example C, m is positive to the left of A, but it's small, And to the right of a, m is positive still, but it's bigger. Right? So as we move through a from the left to the right, m is always positive, but it's increasing still because it's going from small to big. And that means that this derivative, partial m partial x, must be positive still. Okay, and then for d, well, to the left of a, m is big, still positive, but big. And immediately to the right of a, over here, m is positive, but small. So m must be decreasing because it's going from positive big to positive small. So m is decreasing, and that means that this derivative is negative. Okay. And of course, what I hope you noticed is that for number 3 here, comparing part 1 and part 2, whenever this derivative is positive, the vector field is flowing away from the point A, and whenever this derivative is negative, the vector field is flowing towards point A. So it seems like for this very simple example, or for these 4 examples with this simple setup where we have a one-dimensional vector field, it seems like this derivative measures flow out versus flow in. Right, so when this derivative, partial m partial x, is positive, f is flowing out, and when this derivative is negative, f is, I should be using capital F's, f is flowing in to the point. All right, so somehow this derivative is measuring whether the vector field is flowing out or in. All right, so for number 4, use our formula to determine whether f flows in or into or away from these points. Well, first we need to calculate our the quantity that we decided will tell us if it flows in or out. So that was this derivative, partial m partial x, which is going to be cosine x, right? And then we can evaluate it at these points. So partial m partial x, evaluated at minus pi over 2. Cosine of minus pi over 2 is 0. Okay, that means that in total there should be no net flow near minus pi over 2, right? Okay, so now let's evaluate this derivative at 0. Well, cosine of 0 is 1. And we decided that when this derivative was positive, the vector field flows away from the point. So near 1, the vector field should flow away. Sorry, near 0. Near x equals 0, the vector field should flow away from x equals 0. And then finally, when we evaluate this derivative at pi over 2, cosine pi over 2 is 0. And so again, we should have no flow into or out of pi over 2. Okay, so well, let's now for 5, let's actually sketch this vector field to see what it looks like. So I'll do it in red. Let's see. Sine of 0 is 0. Okay. This dot right here, we could make this pi over 6, I guess. Sine of pi over 6 is a half, so that's a little bit positive, like this, say. Sine of this point right here is going to be pi over 3, I guess. 2 pi over 6, pi over 3. So sine of pi over 3 is root 3 over 2, which is, it's bigger than a half, but it's less than 1, so maybe we'll write it like that. At pi over 2, it's 1. And at this spot's going to be 2 pi over 3. So that sine of that is root 3 over 2 again. Okay. At minus pi over 6, so this is minus pi over 6 right here, we're going to get minus a half and then minus root 3 over 2, and then minus 1, and then minus root 3 over 2 again. Okay. Now let's compare these two. Right? The whole idea is to compare these two to see if if what we calculated is matching what we see in the picture. So if we look near 0, right, to the right, the vector field is flowing to the right. To the left of 0, the vector field is flowing to the left. So this vector field is definitely flowing away from x equals 0. And that confirms our calculation, right? Near pi over 2, to the right, it's flowing out, away from pi over 2. But to the left of pi over 2, it's flowing into pi over 2 at about the same rate, evidently, right? Because these two vectors are the same length. So it seems like on net, in total, there's no total flow into or out of pi over 2, since the flow out looks like it's the same as the flow in, and that verifies this right here. We have no net flow at x equals pi over 2. And then the same thing is happening at minus pi over 2, but things are flowing left. But again, there's no net flow because the rate flowing into minus pi over 2 is the same as the rate of the flow out of minus pi over 2. So again, that verifies this calculation that there's no net flow into or out of x equals minus pi over 2. All right, so the point of this example is just to build our confidence that we have correctly identified a way to measure the flow into or out of a point, or the flow of a vector field into or out of any given point. All right, of course, this is still working with this simplified one-dimensional example. So the next few examples are trying to generalize this to full-blown two-dimensional vector fields. So we already know that partial m partial x measures the flow that we want. But if we look at this vector field, well, partial m partial x is 0 for this vector field. But on the other hand, this vector field is definitely flowing away from the x-axis, right? Because above the x-axis it's flowing up, below the x-axis it's flowing down. So this partial m partial x, this can't be the whole story for measuring whether something is flowing into or away from a point, because it's saying that the flow out of the x-axis is 0, when in fact we can clearly see it's not. This vector field is flowing away from the x-axis. What we've missed is, of course, we haven't looked at the function n, right? When we have a two-dimensional vector field m comma n, whether it's flowing into or out of a point probably depends on both coordinates, not just one. So let's think about, well, what could be changing in the y direction to cause flow out of a point? Well, if we look at this particular example, right, below the x-axis it's flowing down, above the x-axis this vector field is flowing up, and so it looks like this function n, the n function, is it's increasing as we move upwards. So the rate of change as we move upwards would be partial n partial y. So for this example, partial n partial y is positive, which you can see, right? Partial n partial y is actually 1 in this case. And that is causing flow to be away from the x-axis. So maybe what we need to do here is add a contribution for the vertical direction, right? Partial m partial x, this is measuring horizontal flow in or out. If we need to also measure vertical flow in or out. So maybe we should add partial n partial y. Okay. So if we calculate this quantity for this vector field, what we get is, so the partial derivative with respect to x of our m function, which is 0, plus the partial derivative of our n function, and our n function is y, so partial y is 1, so we get 1. And this is positive, which should lead us to believe that this vector field actually is flowing away from not just the x-axis, but actually every point. And actually that's true, because if you look at some other point, well, the vectors below are flowing into this point, since they're shorter, they're flowing in at a slower rate than the vectors above are flowing out. So it does seem that there's net flow out of this point. And if we look down here, same thing. The vectors above are flowing down into this point at a slower rate than the vectors below are flowing out. So it does seem like this vector field is flowing away from every point on net. And so it makes sense that we got a constant for this quantity. All right, how about for this vector field? So let's compute this quantity and see what we get. So partial x, so derivative with respect to x of the x coordinate function, which is x, plus partial of the y coordinate function, which is y, with respect to y. Fortunately, these derivatives are all easy. They're 1 plus 1, so that's 2. So again, this is positive, so this should lead us to believe that this is flowing away from every point, and indeed it is. Near the origin, it's clearly flowing away from the origin, but even away from the origin, right, on average, vectors pointing out are longer than vectors pointing in, and so this vector field is flowing away from from these other points as well. And this reasoning works no matter what point you pick. Okay, so that's pretty successful. One last example. Let's look at this thing. Now, for this example, I think it's much harder to tell what's going on, given any particular point, whether the vector field is flowing towards or away from that point. But, that's why we came up with a formula so that we can calculate what's happening when we can't tell visually just by looking. So let's calculate partial m partial x plus partial n partial y. So the derivative of sine of y with respect to x, that's 0, plus the derivative of x squared with respect to y, that's also 0. So this is 0. So what this should tell us is that this vector field actually on net, it doesn't flow into or out of any point. So that's a little surprising because, if we imagine that this is a velocity field for some flowing fluid, it seems like we should have some net flow into some point. But if you actually pick any particular point and then think carefully about the flow near this point, you always find that there is no net flow into or out of this point, right? A little bit above this point, fluid is flowing out at the same rate that it's flowing in a little below this point, and right to the left and the right, fluid is flowing roughly parallel to this point, so it doesn't really flow into or out of this point. So there is no net flow near any point, right? So, this is having the confidence to really declare that there is no net flow into or out of any point in this example is like, this is why we do a few simpler examples where the answer is clear, to sort of build our confidence that this quantity we've come up with really is measuring what we want it to measure. Right? We have to build some confidence that it's doing what we want, so that if we run into an example where it's hard to tell, we can trust that our computation is telling us the right thing, even if visually it's not clear what is happening.